Let's dive into the exciting world of retraining with MobileNet models. In recent years, MobileNets have gained a lot of attention for their lightweight architecture and impressive performance on mobile devices. So, today, we'll explore how to effectively retrain these models using TensorFlow, and I'll show you how you can implement it in your Android or iOS applications. It's a fascinating topic, especially considering the capabilities these models bring to portable devices. So, let's get started. First up, we'll look at what mobile nets are and why they're so popular in mobile computing. Then, we'll jump into the steps for retraining these models. Don't worry if you're not a TensorFlow expert yet. I'll guide you through the process, and you'll find that it's pretty straightforward. Once we get our model retrained, I'll also touch on how to integrate it into your mobile apps. So whether you're on Android or iOS, you'll be well equipped. Just imagine how powerful it'll be to leverage these models for image classification or object detection right on your phone. So grab your favorite coding environment and let's get retraining with MobileNets. It's going to be a fun ride. MobileNet is designed with efficient on-device machine learning in mind. Unlike traditional models like Inception v3, which can be over 200 MB in size, MobileNets are much more compact. They usually range from a few MB up to, say, 17 MB for larger configurations. Now, this reduction in size doesn't compromise performance significantly. MobileNets still manage to achieve decent accuracy, all while requiring fewer operations. This makes them perfect for mobile applications, particularly when resources are limited. The efficiency is gained through something called depth-wise separable convolutions, which break down the filtering process into two simpler operations, depth-wise and point-wise convolutions. To begin retraining with MobileNet, the first thing you want to do is set up your environment. Ensure you've got TensorFlow installed, along with any other tools needed for your mobile development setup. Once you have that sorted out, the next step is to choose the specific configuration of the MobileNet model you want to work with. You can select from a variety of configurations depending on your needs. The architecture parameter can be set to one of the following values: MobileNet_1.0_224, MobileNet_0.75_224, MobileNet_0.50_224, or MobileNet_0.25_224. Each of these configurations represents a different balance between accuracy and model size. Now, let's implement the command that will help us retrain your MobileNet model using TensorFlow. This command kicks off the retraining process by calling the retrain.py script, which is tailor-made to adapt a pre-trained MobileNet model for your specific image classification task. Now, the -output graph flag is super important because it defines where the retrained model will be saved for later use. In this instance, we're directing it to a .pb file located in your TF files directory. Similarly, you'll need to set up the -output labels flag. This one shows where to save the label file that corresponds to your new classes. And trust me, you're going to need this file later to help interpret what your model predicts. Next, don't forget the -imagedir argument. This points to the folder that holds your training images, which is key for the model to learn all about the features of the new classes we are introducing. Then we have the -bottleneckdir option. This is where those intermediate representations of your images will be stashed away, and it's quite handy because it really speeds up the retraining process. Finally, there's the -architecture parameter, which lets you choose which version of MobileNet you want to work with. For this example, we're going with MobileNet at a width multiplier of 1.0 and an input size of 224. So, by customizing these parameters, you can finely tune the retraining process to get the best performance possible for your unique application. When you run this command, TensorFlow will kick off the retraining process utilizing the images from the directory you specified. Now, it's crucial to keep in mind that the label file generated will mirror the structure and nomenclature you'd see with larger models like Inception v3. In short, you're just swapping out the backbone architecture while keeping the operational workflow intact. Now, let's discuss something important during the retraining phase. Have you thought about utilizing quantization? When you add _quantize to your architecture, like MobileNet _1.0 _224 quantized, you end up with a quantized model which significantly reduces its size. For instance, a quantized MobileNet typically weighs in around 5.1 megabytes, compared to the non-quantized version that's about 17 megabytes. This size reduction can be a game changer for mobile applications, where speed and performance are key factors. Now, let's explore how we can implement the label image utility to classify new images using our retrained MobileNet model. First, we need to specify the path to our retrained graph. This step is crucial because it contains the structure and weights of our model. Next up, we'll indicate the image file that we want to classify. For our example, this image is located at /tmp/lab1.jpg. All right, so we've got the image sorted. Now we need to define the input and output layers of the model. The input layer is set to input, which is where we'll feed our image data into the model. And for the predictions, the output layer is designated as final result, which typically reflects the probabilities for each class. It's essential to tie this back to what we expect the model to do. Additionally, we should specify the path to the labels file generated during the retraining process. This file maps class indices to human-readable labels, which is key for correctly interpreting the model's predictions. Finally, let's set the dimensions for our input image to 224 by 224 and apply normalization parameters like input mean and standard deviation. These aspects help align our image data with the format the model expects. This setup is really vital for achieving accurate classification and allows label image to effectively process and predict the content of the image. Now, let's take a look at the output format that TensorFlow generates when classifying an image using our retrained MobileNet model. When you run the label image utility, it provides predictions in a structured format. This format includes both the class label and its corresponding probability. For instance, you might see an entry like N0209971 Labrador Retriever 41, 0.8246. This indicates that the model predicts the image is most likely representing a Labrador Retriever with a confidence level of about 82.5%. Now, this probability really reflects the model's certainty about its classification, allowing you to assess how confident it is in its predictions. Additionally, for the same classification task, you may also encounter predictions for other classes. You might see something like N0209960 Golden Retriever 64, 0.14425, and perhaps N0210409 Kuvas 76, 0.10353. These show lower probabilities for these alternate classifications. Understanding these outputs is crucial because they inform you not just of the dominant predicted class, but also give insight into the model's relative confidence across various categories. And let me tell you, this information is invaluable for applications focused on image recognition, like pet photography or even animal identification in videos. Next, we're going to write the command to build the benchmark model tool, which lets us evaluate the performance of our trained models. This command uses Bazel, a build tool that's really handy for compiling large code bases. The -c opt flag here, that specifies we want an optimized build, and that's super important for performance benchmarking, especially in resource-constrained environments like mobile devices. Now, let's dive into the benchmarking process. Once we build the model, we can run it against our retrained models to measure their efficiency in terms of floating point operations per second, or flops. The command will specify the graph file of our retrained MobileNet model as the input, along with crucial parameters like the input layer and its shape. Here's a pro tip. Setting the -show summary flag to true allows us to receive a detailed output of the model's performance metrics. This is essential for assessing how many computations the model needs during inference. All of this is critical when making informed decisions about model deployment, especially when comparing models like MobileNet and Inception v3. It really reveals the trade-offs between speed and accuracy in real-time applications. So, whether you're building a mobile app that can identify dog breeds or creating a smart camera that recognizes different objects, retraining with MobileNet gives you the flexibility and efficiency you need for modern development. As you dive into this exciting journey, don't forget to iterate on your model, test different configurations, and, of course, have some fun with it. Machine learning isn't just about crunching algorithms, it's about enhancing user experiences with intelligent technologies. In the end, retraining models is a crucial skill in today's AI landscape. With tools like TensorFlow and MobileNet, you've got everything right at your fingertips to make fantastic advancements in mobile AI solutions. So roll up those sleeves, get your code ready, and let's make some magic happen in your mobile applications.